Sim2.
Simulating, made simple.
Hi, we are Sim2 and we are the future of patient simulation. If you are a biomedical engineer and in need of test equipment for VSM, look no further than the Sim2.
Our stunning and clean ambergram style logo reads Patient Simulator this way and this way. Our center S's of the logo form an abbreviation for Simulating Made Simple. Taking that down into Sim equals Sim2.
Now to introduce all of the members of Sim2. Start off, my name is Nathan.
My name is Shane.
My name is Nate.
My name is Dawood.
I'm going to get into the importance of the concept design, which makes our design so unique. As you can see, our design is compact, modular, and lightweight. Each module remains independent from each other, but together remains a very comprehensive patient simulating system. Here's a functional block diagram of the working theory of how our prototype is going to work. Now it's pretty comprehensive and it covers a lot of different things, but I figured it'd be best to pare it down a little bit. So instead, we can see that all of those different components can be broken down into three simple ideas: power, the modules themselves, and the processing or the computing that's going on in between them. If we look at it a little bit deeper, we can see how these different systems are connected. We've got the power, which is going to be powering the modules and the microcontroller itself. And the processor is going to be talking to the modules, as well as the modules are going to be talking to the processor. It's as simple as that. Now I'm going to get into more specifics as to our actual plan for power and modules. So first, for power, we've decided on having a 12-volt power reservoir. And the reason for this is that because it's modular, we're going to have it so that each module is only able to be turned on at once, meaning that each module has access to this 12-volt reservoir power at a time. And it's just a simple click of the button for the biomed to change from one module to the other. The plan going forward right now is to use 120 volts VAC coming out of the wall into a 10-to-1 step-down transformer to accomplish a 12-volt VDC at the other side. As part of our modular and compact and lightweight design, we've decided to add a rechargeable battery into the circuit, which connects parallel to the rest of the unit, and the current will be drawn from that battery. Besides the power supply unit itself, there's going to be needing to be power circuits before each of the modules. And in general, this is still a working theory, but in general, it seems like most of the time we're going to just have to limit the current, and this will be done with simple resistive circuits. However, in the case where we need to use op-amps, which might be the case with the ECG, we'll be using something like a rail splitter to take that 12-volt reservoir from 12 to 0 to now positive 6 to negative 6 volts. Finally, our plan for tackling the development of the modules is to have everybody on the same page and working together. However, each of us to go off and be a team lead for each of the modules. So as we have it right now, the ECG is going to be Nate that you met before. The SpO2 is going to be the other Nate that you met before. And the temperature is going to be Dawood. As of right now, our team is in the midst of acquiring new talent, and we're thinking we're going to be putting them onto the NIBP.
Okay, so now to go into the ECG module, we're just going to go over a little overview of what it actually is. So an ECG is an essential tool for biomedical personnel to accurately test and verify the performance of patient monitoring systems. So just to make things clear, we are not making a patient monitor. We are making a patient simulator for the ECG. So we are going to mimic patient vital signs. So to put in perspective of what reading we're actually trying to get, so the way an ECG works is a 3-lead signal. So it's going to be left arm, right arm, and left leg. And the signal we're trying to mimic is a vector. So it's going to be in between, that goes across the heart. The type of reading that we're trying to get should exceed from 0.25 millivolts, and this duration should not exceed more than 0.11 seconds. And if you want to accomplish our goal, the goal is to get that proper reading, and to get that reading, we are going to need an IC 4017, which is a decade counter.
Now on to SpO2. SpO2 measures the blood oxygen saturation, or hemoglobin, which is red blood cells carrying oxygen. Readings occur through light attenuation, where the intensity of light is reduced due to absorption, and photons, which are light particles, are scattered as it travels through the finger or medium. Some factors that affect the accuracy of an SpO2 are ambient light, which is natural, already present light, patient movement, and skin tones. Oxygen saturation of 95% to 99% are ideal for a healthy human, while something as close as 92% could be a sign of hypoxia. An SpO2 simulator compares how much red light and infrared light is absorbed into a finger, creating a ratio through percentage. Variables affecting light detection that we are taking into consideration is the concentration of light particles and the length of this light path. This module will receive red and infrared lights from the top of the clip and go through our simulator into a photodetector or light receiver to analyze the absorption. The bottom of the layer of the finger will have a colored pigmentation to simulate skin tones, and our blinking LED in the middle of this pigmentation will simulate and mimic a heartbeat rhythm. Our heartbeat LED will connect to circuitry and have coding through Python as it goes through a Raspberry Pi Pico system, which will read and display the SpO2 percentage.
As a team of specialized in biomedical engineering, the goal of this specialty is to provide advanced engineering techniques that help doctor diagnose and treat patient better. Now I will provide some information about the temperature probe testing that is one part of the device. Now I will talk about the probe testing when we applying the current to an inductive coil, generates energy, and from that it also generates heat, and we use it in our project to simulate the patient. We will use iron core inductor and probe out a hole for the patient's sim temperature probe. Thermocouple measure the heat to know when the module has reached the desired temperature.
And the final module we're going to be talking about is the non-invasive blood pressure. And if you want to accomplish this, the goal is to create how an RE would react to a blood pressure cuff inflating. And a normal reading would be 120/80, and this simulates how presetting of values of both systolic and diastolic pressures. And if you want to do this correctly, we need pressure sensors to detect certain thresholds of pressure that we are going to be recreating. So as a group, we tried to decide on some milestones that we want to hit after each of these weeks. So after week 3, we want to conclude research and create a development plan strategy, such as ordering parts and delegating which tasks we want to complete. By week 5, we want to have one functional module working. By week 8, we want PSU working with all possible power circuits completed for the respective modules. Week 11, having a working demo, which means all the modules will be working independently. And by week 13, we want to have all the modules to communicate with one another via U-controller.
Sim2.
Simulating made simple.